We're ready to start. Congratulations, you managed to come early in spite of the time change yesterday night. We will use speak up as usual on this number. Last week, we discussed symmetric cryptography as one of the building blocks used to provide security in a cyber infrastructure. With symmetric cryptography, we have a secret key that is used for encrypting and decrypting, and that makes the messages, the ciphertext, invisible or impossible to understand by an attacker. Another function that we started to discuss is authentication by means of a similar mechanism that also uses a symmetric scheme where the two ends of a communicating party own a secret key that is used to create a MAC, what is called a MAC, Message Authentication Code, which is a small block of bits that has been created from the message and the key, and hopefully cannot be recovered unless you have the key. And this is used to verify the authentication by receiving both the message and the tag. And now if I know the secret key, I can recompute the tag. So I have the computed tag, I compare to the received tag. If both are identical, I presume that everything I have received is authentic. If they are not identical, there might have been a transmission error, or simply the message might have been forged, or the tag might have been forged. Here is a very first simple example of how we can compute a tag. Some of you may remember from your old days modulo integer calculation. This is used in coding. Coding is very similar to cryptography, but that's a bit different. The goal of coding is, for example, to add redundancy to a set of message in order to be able to recognize some errors. When you write your credit card number or your IBAN number, there are digits that are check digits that are used to verify that your number is correct. For example, if you make a mistake, if you confuse a 7 for a 1, or if you interchange the order of two digits, 57 becomes 575, then this will be verified by this coding scheme. Coding schemes are based on techniques like this. For example, the IBAN or the credit card number are based on something similar, something like this here. We take a message, M, for example, your number. We do a modulo operation. For example, here we multiply by 58 and we add 100 and we take the modulo P. Modulo is modulo 257. So it has to be a special number. It should be a prime number for the thing to work well. And the residual we obtain, which is therefore a number between 0 and 256. Modulo operation is the remainder in the classical division. For example, here, if I have to send this string of characters, I translate this into numbers, for example, by using the simplest ASCII encoding of letters. So H becomes 48. Those are hexadecimal representation of the character capital H, etc. So I concatenate all of this. I obtain a sequence of hexadecimal digits, which I interpret as a big integer number. I multiply it by 58. I add 180, and I take the remainder modulo 257, and that gives 35. And if this is a prime number, it is known that this is very powerful. We can do a lot of powerful computation on this. In particular here, it can detect any error that affects 8 consecutive bits in this very simple scheme here. So that's a possible idea. Let's try such an idea on creating a MAC. Here, I'm transferring to my bank a message, which is a transfer order. I'm instructing my bank to transfer some money to somebody who did a job for me. I apply this. So I take this whole message that starts at the first capital T, ends at the last capital T. I translate that very much in the same way I did before. I obtain a big number. I apply the calculation, and I obtain at the end F7. This is written in hexadecimal digits. Now, what would happen if somebody intercepts these messages, doing a man-in-the-middle attack, and transforms, for example, the destination IBAN. By the way, the IBAN itself, the 3, 4, or 17, those are the checksums. Those are the digits that verify the entire number here. So if I want the money to go to me, I am the attacker, and not to the legitimate destination, I can simply change here this by putting my number here. Now, the problem would be, in order to do that, I need to recompute it. If I do the computation, I will have 74 here. But if the attacker doesn't know the secret key being the numbers 58 and 180, then the attacker is unable to modify the MAC here, so that the attacker will send a random sequence of two numbers here, and with probability 2 to the minus 257, the attacker will not, 1 minus this, the attacker will fail here, because I am unable to compute the valid tag. So this is how the message authentication works. At least if we believe that it's impossible to forge the correct value here without knowing the secret. For this specific coding system, do you believe that it is possible? So would the attacker be able to forge a tag after observing a small number of valid messages? Of course, the attacker will observe a large number of messages, because the attacker, so far, we assume that the data are in clear text. I close the poll in a few seconds. And the majority does not believe that it's very secure, and you're perfectly right. In fact, for such a simple coding scheme, it's by seeing two different messages, we can compute the key. So the key here are the unknown A and B, not the modulus, but A and B are unknown. Then modular arithmetic, when P is a prime number, is like regular arithmetic. So if I see two messages and their tags, I see M1 and T1, M2 and T2. So they satisfy this set of equations, and it's two equations with two unknowns, A and B. So I can invert those equations. I can solve this by using whatever classical method you would use. I need to take an inverse modulo P. If P is a prime, that's perfectly doable and easily doable. In fact, it's simple algorithms will do it. So here it's the attacker, after seeing two messages, will find the values of A and B, and of course will be able to compute this number here. By seeing a few messages like this one, the attacker will compute the value 58 and 180. So that's an example of a bad tag technology. Of course, the cryptographic tags are not based on this. Why is it bad? Well, because there is some mathematical structure that makes it possible, after seeing the complexity of the system is fairly small. We need only two integer numbers, A and B. And it's possible mathematically, after seeing a number of messages and tags, to invert the system and get the key. So the trick of creating message authentication codes is to make systems that don't have that property. We say that they are collision resistant, collision being a case where I have a tag that is given, I can modify a message to keep the same tag, for example, here. There are many MAC techniques that exist, but one that is very widespread uses AES or any block cipher. Remember last week we saw a block cipher. Block cipher is something that encrypts a block of 128 bits into an encrypted bit, such that we have done sufficient complex manipulations that we believe that the output is completely random if we don't know the key here. So we use this as a building block in a chained fashion, very similar to what we call CBC AES, but it's a different thing here. So we take a message M. We first compute the length of the message in a number of bits or bytes, and this is used as the seed of this. We apply AES to the length, and the key. That gives us a first number, which we XOR with the first block of 128 bits of the message, and we continue. And at the last part here, we pad the message so that the message is an integer number of 128 bits. And at the end, we obtain the final tag here. So it's very similar to what we did with AES, except now the purpose is different. We're interested not at the result of all encryptions. We're interested only in the last one. It doesn't have the properties of block ciphers that if I see that, because we chain the things one by one. So this is an example of MAC technology. It's called based on AES. And it can be shown that if AES is secure in the sense that we saw last week, that is that it's impossible to have more information about the clear text than anybody who does things at random, if we don't know the key, then this also has the implication that this MAC is unforgeable. So the attack that we saw against the banking message cannot be done with this here. So even if you see lots of messages and lots of T's, you will not be able to undo this thing because the building block of AES is very hard to invert, and therefore, the chaining makes it worse here. So this is how it looks in practice. The second difference with the toy MAC that I showed a minute ago is that the key is, of course, much longer. Here, the key is 128-bit, which is the same size as an IPv6 address. So it's a long string of hexadecimal digits. And this is what is done when we go to the bank, for example. When you do an e-banking transaction, the elements of the transaction will be authenticated with such a mechanism here. Of course, the MAC is not designed to provide confidentiality. We don't hide the message. In fact, the message that I saw here is sent in the clear. And so is the tag, because we need the tag. We need to verify the tag here. The tag alone cannot be used to recover the message. Why is it not possible to simply send this and guess and have the destination recover the message? Why is it impossible in general? Well, by the pigeonhole principle, the length of the message here can be much longer in general than 128 bits. So the number of messages here, the length of the message is longer than that, which means there are, in theory, a larger number of possible messages than there are numbers of possible values of the tag. So you cannot have a one-to-one mapping. There must be different messages that have the same tag, because there are more possible messages than tags. So having the tag cannot be used as an encryption scheme, except if you would limit yourself to having messages of length less than or equal to 128 bits. So collisions will always be possible. But here we just count on numbers. Collisions, that means two different messages that would have the same tag. There are, in fact, a large number of strings of characters that have the same tag as this one here. But hopefully, the probability that this happen is difficult if the MAC is secure, because the bit we require here that the length is long enough. So in order to find a collision here, one way, just like we have in cryptography for the attacker, would be to try all the possible messages and try to guess. Of course, if we have a tag that verifies the authentication, that doesn't mean that we're happy with not hiding our message away from the attacker. So we need usually to combine both. So we will usually need to do encryption and authentication here. And that is, we will now discuss an illustration of the kind of many, many small questions that are asked when you design a cryptographic system. Here the question is, here are three possible ways of combining encryption and MAC. Which one should I prefer? This one is the normal, simplest way. I have a message. I'm sending it to you. I want you to be able to verify that it's correct. So I add a tag to it. But I also want the attacker to not gain information about the message. So I encrypt it and I send both. So an attacker who plays a man-in-the-middle attack will see the encrypted text and the tag. Both are simply random strings of hexadecimal digits. So hopefully, the attacker will not gain any information by seeing them. I can combine in different ways. Here, I'm assuming the MAC and the encryption are two systems that have different keys, which is usually the case. I could also say I first compute the tag, and then in order to perhaps increase security, I use the tag and the message, I concatenate the two, and then I encrypt so that the attacker will see a ciphertext, will not even see the tag. Perhaps that's stronger because the attacker doesn't see the tag. Yet another method is to encrypt the message, send the encrypted text, and then apply the tag to the encrypted message here. Here it's a bit stronger also because we believe that the tag here will be visible to the attacker, but the tag for somebody to forge a tag here, seeing the ciphertext here we need to be able to apply the encryption here from the clear text here. So we're not able to derive T directly from M if we don't know the key of the ciphertext here. So there are three possible combinations. Is any combination better or worse? Yeah. Well, it's hard to say in general, but there are, in this specific case, a problem which is called the chosen ciphertext attack. So this is an attack that has been revealed, among others, by our colleague Serge Vaudenet of EPFL here, where in fact, what I said in theory is true if the messages we send are random strings of bits. In particular, encryption is perfectly secure, not perfectly, but as secure as we can hope it to be, if the message we're sending is an arbitrary sequence of bits. In reality, it is not. So there is always some structure, and the structure can leak some information. For example, if I'm encrypting an IP packet has a lot of known structure. It's always a certain format. It starts with an IP header, then a TCP header, and there's very little variability in this. Also, there is padding. All the block ciphers use 128-bit blocks, which means we need to pad and in order to make this an integer multiple of blocks here. Now, what happens if there is somewhere an error in the padding? For example, you submit a system that is not correctly padded, doesn't have the correct number of bits. Or if you receive an IP packet that doesn't pass the checksums, you try to decode the IP header, and you found that it doesn't make sense. There is a version of IP, for example, which is IP version 9, which doesn't exist. So there can be what is called protocol errors that would cause the recipient to abort and give some information. By giving some information in such cases, if you have a very, very clever cryptanalyst like our colleague Serge Vaudenet, then you're able to get some information. For example, he applied this to AES-CBC. By manipulating the ciphertext and looking for padding error, you are able to recover a few bits of information. And by doing it zillions of times, you can decrypt an entire message if you're able to access the cyber system, the decryption system, a large number of times. Which is why also one of the security measures is to not allow you to try, for example, a password as many times as you would like, because by doing millions of times, that can be used by an attack here. That's an example of an attack that can do it here. If we combine this with the different choices we had, then it's useful to look at the reverse side of the story, which is what we need to do at the receiver when we receive the ciphertext and the tag. If I did it in this way, in order to verify the tag and decrypt the message, here I need to do two things. I need first to decrypt the message, and the tag which was applied to M needs to be applied to the result of my decryption here. So I need to first decrypt the message, then apply the tag to the decrypted message here. Now, in this case here, I see that I start decrypting the message before verifying anything. So if the message has been manipulated, one of the attack will be consisting in taking a C and a T that are legitimate. Then you will modify a bit the C by modifying the padding, the things that can be modified in the ciphertext and submit it to the decryption system. And the decryption system will complain by sending error messages. That's the Serge-Vaudney attack. So the Serge-Vaudney attack will be possible in this case here. In the second case, let's see what we need to do. We have the message that gives the tag and the ciphertext. I need to recover the ciphertext and the tag. So I will first decrypt here, which will give me the computed message and the computed tag, the result of the decryption here. I will compare the decrypted tag to the MAC, to the computed tag applied to the computed message. And if everything is equal, things are fine. So this is how the receiver side will operate. You will see that similarly here, the decryption can be applied before verifying anything. So if the attacker is able to manipulate the ciphertext to cause error messages, that will happen the same way as here. Let's look at this third method. How do I do the receiver function? I have C and T. I can here do two things in parallel. I can decrypt C, which I can do here, but also in order to verify the tag, I need to apply it to the decrypted text. So I need to verify the tag. I need first to have the decrypted text. So I will verify a tag here on the ciphertext here. Sorry, the tag here is verified on the ciphertext. Well, that's what I do first. Now I need to apply the decryption. And if the tag is equal to is valid, only then I will apply the decryption, which means that here, this attack that we said before is not possible because in order to apply the decryption, I have first verified that the combination of the ciphertext and the tag are valid. So manipulation of the ciphertext by the attacker on existing ciphertext and tags are not possible. Yes? Well, here you receive the ciphertext and a tag, but the tag was applied to the plain text. So in order to verify the tag, you need to recompute the tag computation on the plain text. In order to obtain the plain text, you need first to decrypt. So that's why you need to do it first. So what looks like the obvious simple way here, and which has been done, this is implemented in old versions of SSH. Then we find out after the fact, by having cryptanalysts do it, that this is more susceptible to some attacks than this one here. So the conclusion is that today, the RFCs, the IETF, instructs new versions of TLS. TLS is the transport level security. That's what we do when we encrypt over TCP. We should do it in this way, but there's lots of software that does it in this other way. Again, we're not doing a course on cryptanalysis here, but that is an illustration of exactly what happens in the domain of security. We have building blocks that do that give some security functions. Then we have ways of combining the building blocks with things like protocol headers, padding, etc., and combining encryption with authentication, so combining the building blocks together. And then the attackers, who are infinitely smart, will always find a way in the combination to break the system, which is what is possible here. Therefore, the researchers, who are equally infinitely smart, will try to find a way to circumvent this. Take-home message: don't invent your own security mechanism. Even if you have a library that does AES, CBC AES, don't believe that you can do that into your smart grid system in your PMU and you're happy. No, what you need to do is really follow the state of the art by looking at the NIST standards. So there are security standards that will tell you what is today the systems that are believed to be secure. And again, we find the thing that what is believed to be secure today might not be secure tomorrow. For example, here, this mode of combination was believed to be secure for many years, and a lot of TCP-IP software was just using that. Then an attack was known, and then we had to move to this thing. Voila, that's about the Mac. A few questions to keep us going. Oh, I should open it. I close the poll in a second. Closing. There's a tie for A and B. Well, here that was an easy question if you think about it. A passive adversary means some adversary who just looks at the message and gains information by looking at the message. But the goal of the Mac is not to protect against passive adversaries. Everything is sent in the clear, so anybody can watch everything that happens. The goal is really to protect against active adversaries. Right? Passive adversaries will do whatever they want to do, but an active adversary is somebody who tries to modify the message, like we saw in the bank example. We're trying to modify the destination of the bank transfer, and that is what we want to prevent against. That's exactly the goal of the active adversary. In the context of a smart grid, if you have messages that contain measurements, for example, that's exactly the easy way to attack a smart grid or even a non-smart grid. If the messages are not authenticated, then you simply change the values. And by changing the values, you have wrong information that are sent to the control centers. For example, they will believe that the power flows on the lines that cross Switzerland to Italy are at 50% of the capacity of the line. So they might do a load flow that will change the power flow such that this line doubles it or increase by 30% or 60% the power flow. But if in reality the line was close to capacity already, it will simply trip somewhere, it will burn or have too much current on the line.
Sorry.
Yes?
That makes none of the answers because you said it's not secure against passive.
Well, it is secure in the sense the passive adversary cannot do anything.
Okay.
The passive adversaries, they just see the information, but you've authenticated it, so it's they gain nothing. And it's not confidential. If you do just authentication with a Mac, you do not provide confidentiality. You just see the thing. As we have discussed, in practice, when you do a banking transaction or a smart grid monitoring system, you certainly want to have, you probably want to have both confidentiality and authentication. And confidentiality will be provided by, for example, CBC AES, crypto system that encrypts the full message. And we've discussed how to combine the two. Last question. I close in a few seconds. Closing. Majority says C, which is the correct answer. So that was just a provocation to make sure you don't do the confusion between the different uses of AES. AES is a building block. It's a block cipher that is used to create a stream cipher that is able to encrypt any text by chaining or using a counter. So CTR and CBC are the ways of adding a nonce to AES to make it resistant to chosen plain text attack. That's exactly the thing here, which has nothing to do or is not the same thing as the use of AES in a CBC MAC. It's very similar. We use the same building block. We chain it in the same way, but we derive something different, which is a tag with CBC AES. Here we use CTR or CBC AES as a nonce mechanism to encrypt a long message that is more than one block here. So it, by nature, the goal is to allow A, and it's by using a nonce, they rule out chosen plain text attacks. I recall that a chosen plain text attack is an attack where we have seen a number of encrypted messages being transferred, so we can repeat them. And since they were correctly encrypted, even if you don't know the key, if you saw the plain text and the ciphertext, if there is no nonce, then you can play them again. So this is not possible through this mechanism. Okay, what we have discussed today, I would say, is last century or pre-1970 cryptography. If you want, the cryptography that was used in World War II with the machines, Enigma, etc., with more or less sophistication. And the more powerful the computers are, the more sophisticated the systems are. So today we have seen AES, which is the most widespread use. In the future, there are big questions on whether quantum computers will be able to break things like a number of systems. So there might be new systems that come, although AES is believed to be safe even against quantum computers. But the major change, the major innovation that led to the success of the internet, of the commercial internet, is here. That is asymmetric cryptography. So that's really a name changer. Symmetric cryptography requires that the secret key is shared between the two ends here. And now the question is, how do we generate and distribute the secret keys? When you do a transaction with your bank, you need that you and your bank, you share a secret here. So how do you get this secret? If we did not have asymmetric cryptography, you would need to take an appointment, go to the bank, visit your banker every few months to receive a small piece of paper that would have a secret key that would change every few months, and that would be very painful. Instead, you don't do that. You probably went once to your bank, or even not even. You can open a bank account over the internet, and still it works here. And the key thing is that we can have asymmetric cryptography, also called public key cryptography. So it can be used for all the things we've seen so far, encryption or authentication. Now it receives different names. In particular, public key encryption is the equivalent to symmetric key encryption. And what we've just discussed of the MAC, when we use asymmetric cryptography, will be called what is a digital signature. So what is public key encryption, which is the main building block of this part of the story? Well, it's very similar to before. We have a message that we want to encrypt here, but there are now two keys that play different roles. In symmetric cryptography, we have the same key for encrypting and decrypting, and that key must be secret. It's very important. If it's not secret, everything is broken. Here, in contrast, we have a key for encryption that need not be secret. In fact, its goal is to be public. So it is public, for example, posted on a website. So it's well known. For example, it's the public key of your bank here. So everybody knows it. And if you don't know it, there are simple ways to get it, as we will see here. But the private key here, which is a different one, is secret here. So we have what we call a key pair, private, public here. And we still want the same thing as before, that an attacker who sees the ciphertext here cannot decrypt it. Of course, everybody can encrypt because the key is public. The capital key, the public key, as the name gives, is public. So anybody can encrypt. But once it is encrypted, you see a ciphertext. And the only way, at least as long as the system is not broken, the only way believed to work is to know the private key here. So that provides confidentiality in the sense that if I send to my bank a message, I encrypt it. So my text is secret, or I would like it to remain secret. I encrypt it with a public key. Of course, I don't publish P. If I publish P, then it's no longer a secret. My goal is to keep it for me. Then what I make public, or I send over the internet, and is therefore not guaranteed to be secret, is encrypted with the public key. Now, the bank will receive this, like anyone will receive it, but only the bank has a private key and is able to decrypt you. The first system that deployed this technology is called RSA, from the name of 3 authors, was done in 1977. And this one is very similar to the scheme we saw before that did not work for the tag, but here it works. It's also based on modulus arithmetic. So we take an exponent, which is, for example, this, a prime number, which is a power of 2 plus 1. It must be a prime number because all of this arithmetic works only if we have prime numbers. And a power of 2 plus 1 is just a convenience because that makes computation very simple. For example, when you exponentiate to a power of 2, it's very simple because I can do repetitive exponentiation. If I want to ask you to calculate x to the power 8, you can compute x 8 times by itself. But that's not the smart way to do it. Instead, you can square x, which gives you x squared. You can square it again, that gives you x4, and square it again, that gives you x8. So in 3 operations, you have x to the power 8. Here in 16 operation, you have x to the power 2 to the power 16. And if you need x to the power 216 plus 1, that gives you 17 operations. So we have a very large number, but we don't have 60,000 operations to do, only 17 here. That's why we have things like this. Now, the key thing is that we are giving you the secret key, which is 2 large prime numbers. So RSA is based on the theory of prime numbers. And it assumes that it's easy to calculate prime numbers that are very large, which is true. It's not easy to know how many prime numbers there are. But if the goal is only give me a prime number that is 2000 bit long, then that can be done by your RSA software easily. And then the secret key is simply a pair of 2 such large prime numbers. And the public key is nothing else than the product of the 2. So, well, wait a minute, there must be a bug somewhere. Is it that simple? Well, if I give you P and Q, of course, it's completely trivial to compute PQ. That's multiplication. The other way around turns out to be a difficult problem. It is the problem of factoring a number. I give you a number, K. Of course, if the number is 5 digits or 10 digits, that would be easy. We all did that in high school, find the prime number, the prime factors of a number. That's easy to do if the number is small. Here with RSA, we're talking of numbers that must be, to be secure today, of the order of 2000 bits. So much, much larger than IPv6 addresses. And for such huge astronomical number, the best known factoring algorithms still take astronomical time. So even if you take the public keys that are available in the world and you try to break them, it will take you time that is not available with all the computers of the world for many years to come here. But people believe with quantum computers, it could be much better. The quantum computers that are large enough to do that are not yet available. But when they will be available, this theory will go away, but there will be other one that will do similar things. So we believe that giving capital K is, except if you're very lucky, it's quasi impossible to get P and Q. And then how does it work? Encryption simply consists in taking the message M to the power E, and we've seen that as an easy thing, modulo K. So K is a large number, very, very large number, 2000 bits, order of 2000 bits here. But computing the remainder modulo something is a very simple thing. It's division. You do the division that we learn in primary school here. So even for very large numbers, that's a very simple and very fast thing. So the encryption is given by that. Now, so far, that everything's simple. Now, the trick, which is based on the so-called Chinese remainder theorem, consists in doing the following here. So I said the private key is PK, PQ. In fact, what we need is to take the product of P minus 1 and Q minus 1. You can ignore the least common multiple if we don't want to be optimal. We take this, which is P minus 1 times Q minus 1. And then we take the inverse of E modulo this number here. So K is put in red, means it's secret. In order to get K, you need to factor capital K. Factoring it is, we believe, a hard thing. So K, you don't know what little k is. It's the multiple of this, of these two things. So remember here, we have numbers that are astronomically large. So it's one of those astronomically large numbers, and there is a more than astronomical number of such possibilities. And then the Chinese remainder theorem tells us that if I take the ciphertext, which is m to the power e modulo k, if I put it to the power f, I will have, so far that's easy to understand, c is m to the power e, so c to the power f is m to the power ef, modulo k arithmetic is the same as the standard calculation we're used to with real numbers. And then the Chinese remainder theorem says that if e and f are inverse modulo little k, then this is equal to m. ef is the same as 1. We don't have enough time to go through that. If you're interested, there are easy references to find that. So it is based on this number theory property that we will recover the plain text by doing this here. Multiplicative inverse is also something similar, simple to compute. It means it's a number f such that f multiplied by k is equal to 1. That's the definition of an inverse, but it's 1 modulo the modulus here, which is capital K here. So that, sorry, little k here, which is something easy to do here. The only hard thing is to factor. So this property here makes that if I know little k, if I receive the ciphertext C, by a very simple operation, I need to compute something to the power f. It's not so simple because f might not be as nice as this one, but still relatively short operations, I can recover the message back. Of course, I mentioned that we need very large numbers. If I have to give you 10, 10 is the product of two prime numbers, 2.5, but of course that is not very secure. But if I give you this number, then it's another story, and that's the kind of numbers that we will use with RSA. Yes?
From what I understand, there is only one private key works with that public key.
Correct.
So it's like, so for a bank, it doesn't make any sense because you only have one client. Or
No. It's the private key. It's the private key of the bank. You can encrypt with the same public key as I can encrypt by sending to the bank, but only the bank will be able to decrypt. Now, if we collude, if I give you my message, you will get it, but that's my problem if I give my confidential information to you. Let's see a small example. Of course, I repeat, those examples make sense. Doesn't make sense because the numbers are small, but I will see how it works. If the secret numbers are 3 and 11, I do the product, I obtain 33. Again, that's a joke because 33 can easily be factored out because if the number is small, you can use what is called Eratosthenes algorithm. You try all the possible prime numbers that exist before, and then you will have it. But here, but for large number, as I said, that will be hard. So the secret is 3 and 11. If we apply the algorithm, 3 minus 2, 1 is 2, 2 times 10. So we can do the product, 2 times 10, that gives 20. Or if we want to simplify the calculation, we take the largest common multiple of 2 and 10, which is 10 here. So that is the most efficient secret key, 10 here. From this, we derive the decryption exponent, which has to be the inverse of E. E is 7, modulo 10 here. So what is the inverse of 7 modulo 10? And it is 3. Because 7 times 3 is 21. 21 modulo 10 is 1. So that inverse exists. So 10 is not a prime number. Not all numbers have an inverse modulo 10. For example, 2 does not have a prime number modulo 10 because 2 times dot anything is never equal to 1 modulo 10. It never gives a number that ends up with a 1. But the theory says that if we do things as prescribed here, that will always be an invertible number here. So the decryption exponent is 3. So if I receive a message, M, that I have to encrypt, I compute it to the power 7 modulo 33. When I receive a ciphertext, I compute it number 3 modulo 33. This is how RSA works. So if I send this string of characters here that I here let correspond to those blocks here, I compute to the power 7 modulo 33. That gives me those numbers here. Here everything is in decimal. And if I take to the power 3 here of this number here, I will get this again. This is how RSA works. As I mentioned, it requires the keys to be very large. For a long period of time, it was believed that a key size of 1,000 bits would be sufficient. Now people start having algorithms that are able to find, at least with a huge amount of resources, but in a reasonable time, can decrypt up to 1,000 bits key length here. Because as you can imagine, I mean, finding decomposition into prime number is one of the oldest problems that a lot of energy has been put into factoring out. In particular, quantum computers will be able to do it when they have at least 10,000 qubits, where today they have perhaps 50, 60 qubits. So we don't know, but there is a risk that this happens in some future. So what people will do is use other techniques like lattice cryptography, which are similar in what is obtained, but the algebra, the number theory is replaced by more exotic things like lattice cryptography, which is more complicated than number theory and cannot be explained in a few minutes like I did before. So this is how the magic of asymmetric cryptography works. Why is it magical? Well, we'll see several applications. The first one is hybrid encryption. That solves the problem of distributing the key. Now, the price to pay for asymmetric cryptography is that it is fairly expensive in the decrypting side here. So it is doable. It is not taking hours of computation, but it's also not microseconds like AES. So we're talking of time that is order of tens of milliseconds per message here. So you don't do that when you stream data from a PMU to a PDC, for example. You will not encrypt using asymmetric cryptography for every message, which would be nice. We just put the public key of the PDC into all the PMUs, and then they encrypt everything. And then the attackers cannot modify cannot read the messages. Modifying, we'll talk about it in a second. So one of the applications of this technology is to do what we call hybrid encryption. So assume you want to transfer money to your bank and using AES. So we will encrypt everything using AES, but we will derive the encryption key of AES from asymmetric cryptography. Assume I know the public key of the bank, then I will simply choose a random session key. For example, a session for AES, a key needs to be 256 bits. So I will ask my computer to compute at random 256 bits. Has to be truly random. It should not be like the name of your cat or something like this. It should be a truly random number. That there are techniques in computers to find numbers that look truly random. So L is a random number, and that's my key. Now the problem, it's a secret key, symmetric cryptography. The bank needs to have the same. If I send it in clear text, of course, the attacker will see it and the thing is defeated. So I will encrypt it with the public key of the bank. That gives the message Y, and the bank will receive it. Now, only the bank can decrypt this, can recover the L, which is a completely random sequence of bits. So the attacker, if the attacker sees that, will not be able to recover L. So now that the bank has received that, the bank knows L, and I know that the bank knows L without ever exchanging L on the line here. Therefore, I can encrypt my message, and the bank will decrypt using the little L that exists here. So this is how cryptography is used today when you do banking transactions or anything on the internet here. Yes, question?
Yeah, but it's still the bank still needs lots of power on sounding to
So the expensive thing is here, but you do it once per session. This is why it takes some time. When you establish a session, you will see that the banking takes several seconds before the session is established. But you will not do it for every message. Now, if you had only one message to send to the bank, probably you would not need this, but you want to encrypt everything, all the web page, including the videos and everything that are sent. So you typically do that for every message that you send, and you pay the price only once. In a more industrial network, if we use that, for example, to send commands from a control center to actuators that are repeated every second, the control center sends messages here. Similarly, we will do that once every few minutes or every few hours. That's why it's called a session key. We use this mechanism to derive a key and use it for a large number of messages. Not too long, because we believe that if a key is used for too long, as a passive attacker that has monitored everything, a very large collection of coupled ciphertext plaintext, and can use that to mount it. Well, I think we should perhaps do a little break now. So a break for and to warm up a bit for the next phase, let's do a little quiz. Assume we would use asymmetric cryptography in a PMU PDC exchange. Again, I stress this is academic. We don't do that. We would use hybrid encryption and authentication that we will discuss a bit later. But assume we do that with asymmetric cryptography. To encrypt the message, which key would the PMU use? I close the poll in a few seconds. Dirac on C, which is the correct answer, we will use the public key, which is a bit counterintuitive. We will see other uses of asymmetric cryptography, other combinations for authentication. Now, if we use hybrid encryption, sorry, if we use symmetric key in contrast to asymmetric key, how many keys are we expecting that we need to use in a setting here where we have n devices that need to communicate directly and securely with each other? I close the poll in a few seconds. Closing. And by a short advance F is the majority answer, which is the correct answer here. If we have asymmetric cryptography and n devices that need to communicate with n devices, then every device needs its private key. So we'll have one private key for every device and a corresponding public key. So there will be capital N keys. That's a very extreme cases. In general, it's not true that any device communicates with any device. For example, PMUs communicate with PDCs and not with every other PMU. So in reality, it will be less. But if the number of associations we have is N, we need N keys with asymmetric crypto. With symmetric crypto, we need the number of pairs, which will be N times N minus 1 divided by 2. So as raw numbers, it's order of N squared. So that's the difference. If you have 1,000 devices, you need 1,000 keys instead of 1 million or 500,000 keys, right? That's the difference between asymmetric and symmetric cryptography. Asymmetric cryptography can be used for hybrid encryption. That's the first use for encryption, but is used primarily for authentication in the name of digital signature. We can use it in the same way, but now we reverse the order of the keys. I want, same story as with a Mac, I want to authenticate a message M by sending a tag, or it's called here a signature. Now it's computed in the same way. We have the secret key on the sender part. But now the difference is that if we use asymmetric cryptography mechanism, the key at the destination need not be the same secret key here, but can be the public key of a key pair. And it has the same properties at the tag. In particular, when I receive M and S, I can, with the public key, verify S by reapplying applying the computation of the tag here. And I can verify S, might not recompute it, but I verify that it is correct by comparing to M and a given verification algorithm here, which is not the same as recomputing S here. That's a small difference with the symmetric system. In the symmetric system, the key is shared and the destination can recompute the tag and know whether it's true. Here we'll see the destination does not recompute the signature, simply verifies that the signature is correct, which is a weaker form of a weaker property here. How does it work? Well, if we have RSA, it uses the fact that decryption and encryption properties of RSA are commutative. So this little circle means the composition of operations. If I apply EK first, so I encrypt, then I decrypt, it will give me the same as if I decrypt or I encrypt, because that's one of the properties of number theory of exponentiation. If we look at the details, if you remember what we did, this is all based on exponentiations, and ME to the F is the same as MF to the E here. So we can use that here by saying if I have a message to do, if I have a message to sign here, I will apply the decryption function with the private key to the message. So I treat M as if it would be a ciphertext of a certain, of course, it has to have a certain size, which is not too large here. So we will make it a block using discussions we will have in a minute. Then I compute S here. In order to compute S, because I've used the private key, we believe that it's impossible for somebody who does not have the private key to do the same thing here. I transmit M, and then I will apply the encryption function of RSA to the message here, and the encryption applied to the decryption will give the same thing as in the reverse order. Therefore, what you have computed here should be exactly equal to what I compute here. And if that is true, then I think the message is correct. Again, this is true if the K is large enough. Otherwise, factorization is possible. If factorization is possible, the attacker, by knowing capital K, will derive little k, which of course breaks everything. So this is how we can use RSA by reversing the order. If I use the private key first, that gives a way to guarantee, that what I receive here can have been computed only by somebody who knows the private key. In reality, we don't want to do that to the long text. If I'm downloading a piece of software of 1 gigabyte, for example, I will not apply RSA to this because it will be very complicated. So what we do instead is we compress the message. That's a theme we've seen already with AAS, CBC, etc. But with CBC, it was naturally coming from the fact that AAS applies to blocks of a fixed length here. Here, RSA can apply to a message of any length. But to make it efficient, we want to reduce it, for example, to a size of 256 bits. So how can we reduce it? Well, by using what is called a hash function. So a hash function, which probably you've heard already, is something that maps a message of any length to a short block of, for example, 256 bits. So I take my 1 gigabyte of software on my backup. I do a backup. I want to verify that the backup is not corrupted, for example. I will similarly use hash functions. So I distill my gigabyte into 256 bits, for example, here. Now, hash function doesn't have a key. So a hash function is just a way to transform a very long text into a shorter text. Of course, with some good properties, it must be such that the result, which is called the digest, appears to be randomly chosen among all the possible 2 to the power k values. That is large if k is 256, but much, much less than the possible number of messages because the message is long here. So collisions will always be possible because we have more possible messages than the number of possible digests. There will be collisions, similar to what we've seen with the tags a few minutes ago. But they should be very difficult to forge. And in particular, this should appear to be completely random. And then we apply the signature to the digest. This is how signature schemes are done today in the internet. So once we have the signature, it's very similar to a MAC. I have a long message. At the end, I have a small s. But with difference that we can apply it to asymmetric cryptography here. Remember, this first building block here, the hash, has no key here, it has nothing secret here. Anybody can do the hash here. If I give you the message, the hash is a function that is typically published. It's not a secret function. In fact, in cryptography today, it is believed that it's not a good idea to keep the algorithms secret. It is one of the principles of modern cryptography. Very old cryptography kept everything secret. So Julius Caesar had the Caesar cipher itself was secret. So people would just see a random set of letters. At that time, there was not as smart, or they were as smart as we are today, but they didn't have the same education and the same tools. People did not find it. In the banking domain, people believed for a very long time that it's better to keep all the procedures secret so that the attackers have less information. But today, it's not believed to be a good idea anymore because even if something is secret, sooner or later it will be revealed. There will be leaks, the WikiLeaks, name it, anything that if you keep something secret to the level of the whole industry, it's impossible to believe that there will be one single person in that industry that will make the secret public. Perhaps somebody crazy whose life will be ruined after making it secret, but still the secret will leak. So secrets should be made available only to a very small number of entities. If you make RSA, for example, secret, all the banks in the world will use this secret algorithm. That will not be very safe. Whereas if I go to my bank, it's only my bank that keeps their private key secret. If they lose their private key, it's not the whole banking industry that's corrupted. Question?
Can the middleman distinguish between the signature and the message?
Can an attacker performing a man-in-the-middle attack distinguish where the message and where the signature is? Yes.
Just before?
Yes. So this guy can modify M or can modify S, but then I will verify it. We verify that the signature corresponds to the message. We verify the pair. The signature and the message always go by pair. We verify that this is signing this message. there can be collisions. It is possible. But like for tags, we believe if the system is very safe, is correct, it is very hard to forge such a thing. The probability that this happens will be 2 to the power minus 256.
They have access to the code, so they just know how to like check what will be the
Yes, the public key allows anybody to verify, but it doesn't allow anybody to create a signature. The cryptography is asymmetric. The functions are not the same. The calculations are not the same. They commute, but they are not the same. So anybody can create. The attacker can also send me a signed message signed by the attacker. That's fine. But what I want here is to have a guarantee that the message that this one is signed. So hash functions, for example, perhaps we could recycle our old tag candidate, this one here. We've seen it's not a very good cryptographic system because the A and B can be computed easily, but now there's no problem. The hash function is public. So my long story was about that. In the internet today, we make all the algorithms public. Everything should be public except the secret keys. Because we believe that the protection given by making the algorithms or the procedures secret is weak anyhow. And second, by making them public, we also have all the academic community who can attack them and see whether they are weak. So we believe the academic community is more people than the bad guys. We will see in the future what happens. So here, that's my public hash method. And that will give, for example, if I hash that here, I will give this F7 here. Now it's a hash. It's not a secret. So I would apply then RSA to this for obtaining a signature. However, I can forge this message. So here is the message here. I'm an attacker. I've seen that on the fly. Then it's possible to do what is called mounting a collision. I changed the message. What did I do in the message here? I added some white space, which is a character. It's the white space character. And because this is linear algebra, I can compute what is the effect of how many white space I need to add in order to obtain a given hash. So here I obtain a different hash, F7, but I could even compute the number of white characters that would give exactly the same hash as before here. Because a white character is like adding a digit to adding several digits to my number here. So this is an attack that was mounted by another colleague of ours, former colleagues, Arjen Lenstra, who showed how it is possible to break authentication mechanisms that use hash functions based on hash functions that are too simple, that are predictable here, because it's possible to change it too easily here. So a good hash function should be what we call collision resistant. It means that it's hard to find a message that has a given digest, typically because I want to change the message by doing some manipulation which is, of course, if I apply RSA to if the digest is the same, then RSA will give me the same signature. So if I find a way to modify M such that the digest D remains the same, then of course I have succeeded in attacking the signature scheme. I will transfer the money not to the legitimate recipient, but to someone else, for example. So the difficulty with hash function is called collision resistance. And there are many cryptographic hash functions, and many were proven to be not collision resistant. So you can find tricks like the one I showed before, but even more sophisticated one. For example, MD5 and SHA-0, those are the name of hashing functions that are broken today. And we need today to find SHA-2 or even better SHA-3 here. So once we have a hash function, we can apply it to asymmetric cryptography. We can also apply it to symmetric cryptography. which gives us an alternative way of making a tag. For example, if I have a message M and I have some kind of, I can create what is called a hash-based MAC, which is an alternate. Instead of using AES with CBC chaining, I can do the following operation. I take my secret key, which now needs to be shared between me and the destination here, and I apply this, where the double bar means concatenation. I hash the message and the secret key, which I concatenate with the secret key, and I hash again. So that's an example of a tag that is derived from a hash function. So hash functions are methods that are used to provide authentication in combination with either asymmetric cryptography or alone here when we add a key into it, we're obtaining directly a tag here. Voila, so let's recap some of the things we've seen by trying some more quiz. PMU signs the messages sent to the PDC. Now that's probably more realistic use. The PDC needs to have some guarantee that the message has not been tampered with. For verification, the PDC, what will the PDC use? I close the poll in a few seconds. And the large majority for A, which is the correct answer. So the PMU signs, that means the PMU should have the secret. The way it works is if you want to verify something, the only thing you verify is that the tag or the signature that you see can reasonably only have been computed by somebody who owns the secret. That's how authentication works. If you use asymmetric cryptography, that means the secret is on the signer side and the verifier uses the public key, which of course is a very convenient way. So you can verify that the message you receive comes from your bank, for example, by verifying the bank's public key here. Now, a more technical question. So M and M primes are two messages, one IP packet, for example, here. And here are the kind of things you will read when you configure your system. C, that's a ciphertext, is CBC AES K of M. That means that this is CBC chaining applied to AES with a key M, with a key little k. And C prime is the same key, the same crypto system, and applied to a different message M prime here. So those are ciphertext here. Now, T are tags, which are using what we've called HMAC. So remember, we simply hash by combining the message with a secret key. And here 512 means that's the size of the tag here, of the resulting hash. So I apply the same function here to M and M prime. I obtain T and T prime. Or I do here SHA-3-256. This is there is no key. This is a simple hashing mechanism. So I compress a message M into something that has 256 bits long, and I obtain D and D prime for two messages M and M prime. Which statement is true? close in a few seconds. The majority says G, but the correct answer is H. Not all, but none. So first, B and D, well, that's the pigeonhole principle. When you hash a long message of 10,000 bits into 256 bits digest, well, it cannot be one-to-one. So there will be, if the digests are equal, doesn't mean the original messages are equal. It's always theoretically possible that a collision exists. This is why hashing is hard. This is why something that's believed to be safe today, secure today, might be unsecure tomorrow. If you find a smart way to exploit this collision, then the hash is broken. It's believed not to be broken for SHA-512 and SHA-3, but same thing here. Whether you add a key or not, you've reduced the size of the message. So the digest or the tag here is always smaller than the message. There can be collisions. Here it's one-to-one, it's true. But remember, there is the chosen ciphertext, chosen plain text attack. We don't want that the same message encrypted twice produces the same ciphertext. Yes, yeah. Yes, it's true. But then with AES, we need a block. If it's not CBC, we need a block of the same size. We need a block which is the same size of the output. So it's true. If we encrypt a message which is one block, it's a one-to-one mapping.
It might still be different
Yeah.
size.
Yeah. Okay, we have seen the building blocks, but we have not seen the major silver bullet, which is called the certificates, which are things we are exposed to. So even as users, even if we're not playing with the crypto system, we're exposed to certificates. So what is the problem? Well, you go to your bank, and we've seen that in order to go to encrypt and authenticate the system, we will use session keys here. In fact, two, one for encryption and one for authentication. So and of course, I'm not explaining how we combine the two. We might do them in a smart way. So we typically need two keys. And there are, as we have seen, the principle of hybrid cryptography is to sample the key at random and exchange them by encrypting them with asymmetric cryptography. Now let's see an interesting man-in-the-middle attack. Assume somebody broke into the basement of your building and broke the cable and put an Ethernet switch in the middle so that they can read and insert traffic like we do in the advanced security lab, for those of you who take that version of the lab. So it's very easy to do on non-authenticated or non-encrypted cable system, which today is the case for most cable systems. If the thing is encrypted, if the physical layer is encrypted, of course, that will not work. But here, if a man in the middle, also in a Wi-Fi hotspot, which is public, which is open without encryption, that will be very easy to do. So the man in the middle does the following. Intercepts all messages coming from the bank and replay to you, but by changing the key. So when you receive something which you believe is the public key in the bank, in fact, is the public key of the bad guy. Of course, that requires a sort of James Bond setup where somebody broke into the basement of your building and so on. That's not really James Bond, right? You can do it with tools we use in the lab. So it's not expensive attacks. Still, it's not very common. But another way that is even more common is you receive a mail that your thing is from the bank, and the mail is sent to you by the bad guy, and then the mail asks you to click here, and when you click on something, you don't go to the bank, but you go to the website of the bad guy, who sends you a key, and this bad guy is saying to you, here's the key of the bank, public key of the bank, which I would say is the major way systems being attacked today. having people go to wrong websites instead of the authentic ones here. So once this is done, Lisa believes that she's speaking to the bank. So she will use the public key of what she believes it to be from the bank, sample random session keys, give them to the bad guy. Now the bad guy will do the same to the bank, will pretend to the bank that he is Lisa. Now he knows the random numbers, L1, L2, because he can decrypt it because he has the private key of his own public key pair. And then pretends to the bank that he's Lisa, so replays everything, but of course, by encrypt it now with the public key of the bank. So the bank receives L1, L2 here, this guy also, but now the man in the middle has the secret L1 and 2, which was what we wanted to avoid. We did not want to send L1, L2 over the air. We wanted to make them secret, but now they are not secret. So since he knows the secret, he can take any message that you send, forge it, and re-encrypt it and compute new MACs that will be completely accepted by the bank. So that's the man-in-the-middle attack that is possible with the techniques we have seen so far. So we've seen that the asymmetric cryptography can be used because the key is public, but the problem is how do I know that the public key is really the public key? So we need to authenticate the public key. The public key is used for authentication, but we need to authenticate it here. So we have a chicken and egg problem, but fortunately, like we can build the first egg. Which is how we will solve the chicken and egg problem by what is called using certificates. So a certificate authority is an authority, is a company that issues digital certificates and we believe is trusted. What is a certificate? Well, it's a piece of text that contains essentially the public key. So if your bank is this one, the certificate will contain the description of the bank and the public key. And the public key is signed with the private key of the certification authority. Now you will tell me, well, what's the difference? Now I need to have the public key of the certification authority. But that's already much fewer public keys to have. That means your software needs to have the public keys of all the trusted parties, which are the certification authority. Now, the public key is typically installed in the device or program. For example, your program today is probably a computer, installed in a computer. If we ignore Linux for a second, there are only two brands of operating systems, three perhaps with Chrome, that come from Apple, Microsoft, or Google. So only those three companies, again, if we ignore Linux, need to pre-install into their software the certification, the public keys of the certification authority. This is how things happen. Now, if you install software in a PMU, there will be a similar thing. Your PMU comes perhaps with software installed by a national instrument, and then you must trust the national instrument installed the correct public keys of trusted parties of the certification authorities. Once you have that, then you can go on. Then you can use, you have pre-installed public keys. Now, if you do it from scratch, so if you take a random Linux distribution from you don't know where, of course, you're taking the risk that you have public keys that are forged, that were installed by a government that wants to infect Linux systems, for example. So this is not very satisfactory, but this is the state of security today. The only way the whole system is secure is that the major actors have installed into your system the correct keys. Once in a while, you will find yourself in a situation where the system will see, oh, I cannot verify this signature. Should I install this certificate? Do you want to continue? And the answer should be no. If you want to continue, that means you are bypassing this level of security. So when I go to my bank, the first thing I will use browser. So what I said about the operating system also applies to browser. We go to the internet by using a Firefox or Chrome or Safari or even Internet Explorer or Edge, whatever it's called now. Those also have pre-installed such a certificate here. So if you install a more exotic browser, you must typically install them, starting with a pre-installed browser. When I go to my bank using one of those browsers, I trust that my browser software will verify the certificate and will display something that I can read that says it is verified. So if I see this sign here, with this green padlock here, it means that my browser has received a certificate signed by a certification authority, that my browser has the public key of the certification authority and has verified the signature using asymmetric cryptography here. Certificates have a validity time and can be revoked, for example, because the length of keys 20 years ago are no longer sufficient today. So a certificate that was issued 20 years ago is probably no longer secure. They were using keys that were perhaps 512 bits that can be broken today. So everything has a validity, which means in particular that your time also on the computer must be valid. If your computer believes we are in 1964, perhaps it will use certificates that are no longer valid. Certificates can be, it's not only the crypto system that can be invalid, but also a certificate may be invalid because, for example, it has been corrupted. If the private key of this bank has been stolen, very bad for a Swiss bank, that their reputation is dead. But if that happens, the certificate will be repudiated. There are blacklists, and after some time, at least, it will not be renewed. A certificate is typically valid for 1 year. I don't think I've never seen that it's ever valid for a longer period than that. So that's also another reason for having time here. So so Lisa's browser will use the certificate to verify the public key, and as we've seen, all security derives from there. Once I know it's the public key from the bank, I know it because I trust my system, but also because I trust my eyes that what I'm seeing on the screen is really telling me that this is certified. So some browsers will simply display it like this. Some stronger security-oriented browsers like Chrome will typically refuse to go to websites that are not authenticated. So if you go to a website that does not use certificates, the Chrome software will ask you, are you sure you really want to go there? So that is probably a very old website. The first website I wrote in 1996 was not using, it was an HTTP website. At that time, there was no security. If you want to continue accessing it today, probably you will have an error message. One little question, where does the digital certificate from the bank come from for Lisa's browser? Okay. So very conveniently, while we're doing a quiz, Zoom reset or change server. Let me close the poll. And the majority says D, which is the correct answer. So from the certificate, what we want is the public key, but also the identity, because the public key is binding the who it is the public key from. If the guy is an attacker, the attacker could have a valid public key, right? I am the public key of, I don't know, whatever corrupt mafiosi organization. So the correct answer is to have A and B. Of course, the public key of the issuing certificate sometimes is written in the certificate, but we should not trust this one. In fact, a certificate that contains the public key of the certification authority is called a self-signed certificate and is useless. It's like you ask the police, are you the police? They say, yes, I am the police. But how do you trust that you are the police? You come into my house with a gun. Are you the police? Yes, I guarantee I'm the police. But if you have no external means of verifying that this is the police, that doesn't help. So in real life, people who have the right uniform, who look like policemen, we check them. And if they come with a car that looks like a police car, we trust them. Here, self-signed certificate is used, for example, in a lab setting when you want to test some security software. So we use it, for example, we self-sign the certificates that we use in TLS programming exercises, because certificates need to be paid. If you want to have a valid certificate, you need to pay those third party, the certification authority. Of course, they need to have some revenue from that. So it costs money. Security is a good business model in the internet. So it costs money. So self-signed certificates are used, I would say, in self-tested environment. Perhaps if you run a company like Romand d'Energie, you may have your own certification authority inside your company. You may have 2 or 3 trusted persons who will generate the certificates. As long as you use it only for PMUs and PDCs, for example, that's another use here. But for you and me, when you go to the bank, if the certificate is self-signed, it's probably highly suspicious. In fact, the only reason in the public internet would be to mount an attack against you. Oh. We had lost Zoom, now we have lost the computer. Good. Well, I think it's a convenient time to do a break since the computer failed. So we start. We will conclude this section on cryptography and related techniques by the last building block, which is called the Diffie-Hellman Exchange. And with this, we will have covered all the primitives that are used in today's crypto systems. The problem is the following. So assume we do everything we discussed so far. So we use certificates to get public keys correctly. Then having the public keys, we can generate session keys. And we use session keys for authentication with hash functions or MACs that are secure, hash functions that are collision resistant, etc. So we do everything right. There still remains a problem. Like, assume an adversary has recorded everything. So this man in the middle has recorded all the messages and is not able to do anything with that because we cannot break the encryption. However, as a smart and high capability attacker, we keep the records, we keep the logs of the messages. So the bad guy does not know what is inside the machine on the left or on the right, but has been able to observe some records and then waits a bit. What happens after you wait a bit? Well, perhaps RSA is broken because you have quantum computers, or perhaps simply, if we were 20 years ago, RSA was using short keys, and with more advances in factoring prime numbers, we have found new algorithms that are able to break the keys of 500 bits that we were not able to do at that time. So some years later, we might be able to find the private key because we can break RSA. That was done many years ago with short keys, for example. That's a scenario which is quite realistic. So some attackers, of course, can be short-lived, but some can be long-lived, in particular governments or mafia organizations will keep the logs for some time and wait until something is ripe, some fruit falls from the tree, like a crypto system is broken. Now, what do you have? Well, perhaps if your goal was to attack the PDC by sending wrong messages, well, it's too late. All those real-time messages are too late. However, in the logs, there might be the interaction between you and your Google Mail account, for example, or Google Mail probably use two-factor encryption. So, but some account on some system where you had, for example, passwords. Passwords were encrypting using all the session keys derived from certificates, etc. But now I have the private key. So if I have the private key plus the logs, I can decrypt the logs and I can have some information, which for the vast majority of it will be useless because it was interesting in real time, but might contain some information that is still secret today. So this is how you could reveal and do WikiLeaks and things like this. Or this is also how you could gain, for example, passwords that are still in use, because not everybody changes their password every year, as they should, right? So the adversary has gained because there is no what is called forward secrecy. So one of the high quality security functions we would like to have is not just confidentiality and authentication, but forward secrecy. Forward secrecy means that we're resistant to an adversary who has the logs of encrypted messages sent in the past and the private keys used at that time. I insist we don't assume that the adversary has accessed the content of your computer 5 years ago. Of course, if you have that, you have much more information. Here, we just assume that the adversary has the logs, so things that were copied and were useless at that time, but later could be broken because the private keys technology has changed over time. This can be defeated by another technique, which is called the Diffie-Hellman Exchange. In one version that I show here, it relies also on the number theory. That's not the only version. That, as I mentioned for RSA, there are alternatives that use lattice cryptography that is more powerful, but is more complicated to explain. So here it relies on what is called the difficulty of the discrete logarithm. It works as follows. So the goal is that A and B do hybrid encryption. They want to exchange the private keys, but the way to do it was to, with the other system, was to encrypt them with RSA. But now we don't want this because if we have the encrypted version of the key and we know the private key of RSA, then this will not, this will be able to reveal the secret keys that were exchanged. Instead, we do the following. So we agree on a very large prime number, a bit like RSA. Very large means really astronomically large here. And a generator of the field of prime numbers. So what is that? A generator is a number between 1 and n minus 1, such that any number in between 1 and n minus 1 is a number of G modulo n. So that's a bit a weird thing in number theory, that there are always any, if n is a prime number, there is always one, in fact, usually several, so-called generators. So of course, the easiest way to describe all the numbers between 1 and n minus 1 is by calling them 1, 2, 3, etc. But we can also call them G, G to the power 2, G to the power 3, etc. So I'm giving an example here. If n is equal to 17, 17 is a prime number. If we take G equals 3, and I plot here all the powers of G, modulo 17, so 3 to the power 1 gives 3, 3 to the power 2 gives 9, etc. 3 to the power 5 gives 3 to the power 5, 381 times 3, so gives 243. Modulo 7 is equal to 5 here, etc. If I continue, I find all those numbers. And if I look at this list here, I see that all the numbers on the left appear here exactly once. So we say that G equal 3 is a generator of the integers modulo 17. Of course, we don't have 0. 0 to the power anything is 0. But all the other numbers are obtained as a power of 3 here. And if you look at what it does, it in fact de facto does a random permutation. Now, what is believed, if computing g to the power k is easy, that's a power calculation. The reverse, finding, for example, that 16 is g to the power 8, it is believed that there is no other way today than doing what I did here, doing the whole list. There are criterions to find whether G is a generator or not from number theory. But once you have found a generator, it is believed that there is no way of finding the reverse mapping other than doing it exhaustively, which is trivial to do when n is equal to 17. I have 17 numbers, so that's 16 because we stop at n minus 1. So of course I can do it exhaustively. But if my number is like the numbers I showed before, an integer with 2,000 binary digits, the number of permutation is huge. The number n itself is already astronomical, but the number of permutations of n is factorial n, which is then undoable here. So this is called the discrete logarithm. We say that 4 is the logarithm of 13 modulo 17. Because the logarithm is the inverse of an exponentiation. So that fact being said, we can use this. I have picked capital N here and a generator. Then what we will do is Lisa will choose a random number like we did before. But what we will send is not the random number, but g to the power a. Yeah. And the other side, B will do the same thing. We'll choose a number B and send G to the power B. So we believe that reading the G to the power A or reading the G to the power B is something that is very hard to invert. So I will not know A by reading G to the power A. Then from that, Lisa will compute what it has received, which is now public, to the power A. A is secret here. So Lisa will compute G to the power B to the power A and calls that L. B will do the same thing. B will compute whatever it has received, which is G to the power A. We'll put it to the power B and we'll compute G to the power B to the power A, which by the laws of power is the same. This is G to the power AB. So both are computing the same, but they have sent different messages here. So for example, if A chooses 7, then Lisa will send 11. So B has received 11. B has chosen 13. We'll compute 11 to the power 13. We obtain 7. Lisa has received 12 and computed 12 to the power 7 here. That gives 7 here. Both have the same number, but they've never exchanged anything in common here. So that is how this key exchange will work. So at the end of the exchange, both parties have created a shared secret, but they have not transmitted anything secret because we believe that computing the discrete logarithm is very hard here. So the discrete logarithm has no key. It's not a secret system. We believe it's very hard. Of course, if this is not very hard in the future, we will be able to break everything here. So the discrete logarithm is not used today, but other systems that are believed to be truly safe, at least for several decades to come here. We're almost done, but here we still have an issue, which is the man-in-the-middle attack, again and again. You could replay very much in the same way we did before. We could replay this in the middle and pretend to be the bank to Lisa and pretend to be Lisa to the bank. And that would work exactly because this guy will agree with Lisa on a secret key without ever exchanging anything. But once you've agreed on the secret key here, you can decrypt all the messages that Lisa sends. Then you can agree with the secret key on the bank and say to the bank that you are Lisa. And then bingo, as before, this man-in-the-middle attack will fail. This is why we add in the hybrid encryption, signed a signature scheme. So before doing that, Lisa will do will sign will use signature public key from the bank. So for example, Lisa and similarly, the bank will use the public key of Lisa here. So this is how it will work. Lisa will sample a secret A, will sign it with its private key. And now when the bank receives it, it will be able to verify that it comes from Lisa because it has this encryption here, this authentication by the signature, and vice versa. Now you could say, well, but that will not be forward secret because we use cryptography. We use RSA or ECDH that may be broken in the future. It is true, but the guarantee we want here is that at the time where we do the Diffie-Hellman key exchange, that at this time, we're really talking to the other end that we believe is the other end here. So even if later those keys can be broken, I mean, that will not, at the time where the key exchange was done, the keys, Lisa knew it was talking with the bank here because the attacker that gets the log cannot revert back in time and then lead Lisa to believe that she's talking to the bank because that was done 5 years ago. So this signature is not affecting the rest of the algorithm. It's just affecting the fact that Lisa knows she's doing the Diffie-Hellman key exchange with the bank and not with the bad guy here. So those secrets that are made here are used to create the session key. And as we discussed several times ago, all of these should be used for relatively short amount of time and thrown away whenever a new session key is computed. In particular, they should never be sent in the log. And we assume that the attacker does not have a log of everything that the computer did. Of course, if you have that, you know all the secrets that inside here. So an adversary who has access to the history of the message cannot decipher the message, even if she finds the permanent keys stored at the bank, which are here, because those permanent keys are not used to derive the random number here. They were just used to make sure that we're talking to Lisa exactly. Voila, last quiz of the day. Test your understanding. I close the poll in a few seconds. And the majority says C, A and B, which is true. A, both parties create the same secret without ever sending any secret information on the line. That is true. If an attacker can solve the discrete logarithm, then forward secrecy falls apart. This is true also, unfortunately. So that means that we solve a problem of being able to break RSA keys here, breaking the public key and derive the private key. If we're able to do that in the future, well, forward secrecy will still help us. But if we're able to solve the discrete logarithm, or whatever is used, in fact, which is elliptic curve cryptography, then this will not be forward secret. But this is the state of affair today. And that leads us to the conclusion. So we come to the end of this module, at least for the lecture part. We have seen confidentiality, making things secret. This is provided by various encryption schemes. We've seen AES and the requirement to chain it or to use nonces of other forms. MAC provides authentications using a secret key, and public key cryptography provide way of authentication and encryption that are more expensive to compute, but use asymmetric keys. One of them can be made public. But most importantly, they provide a way to have certificates, which are really the main building block on which security is based today in computer systems, which provides authentication. And also something I did not discuss too much, non-repudiation, which is the fact that once you have signed something with your private key, that's a proof that you signed it. So if you say, buy me 10 tons of whatever, of wood for the next winter, and then you change your mind when you see the wood around, oh, I didn't say 10 tons, I said 10 steers or 10 cubic meters. But you signed it. So if you signed it, I can prove that you did it. That's called non-repudiation. Take-home message for all of us around here, a cryptographic method is important. When you build a smart grid system, a control system for the smart grid, a monitoring system, a measurement system, it should be secure, should be willing to pay the price to use, like we do in the lab, TLS security or DTLS or whatever mechanism. It's a pain. It's more complicated to use it than to simply send the messages using raw socket calls. It's more complicated. It requires to distribute keys and authentication and passwords and user rights and all the like. But you should do it. You must do it. If you don't do it, your system will be attacked almost instantly. When you open a server on the internet today, you can do that. You can download web server software on your computer, do it at home, open the ports on your ADSL modem. You will see that in the next few seconds, your server will be attacked by port scans, trying to find all the possible weaknesses and finding all the ways to get all the passwords that are inside. Within seconds, right? I'm not saying within years or months, within seconds. So the internet is full of attacks, just like our biological system has to have an immune system because the world is full of bacteria and viruses and so on. And for most of them, we survive, and it's no big deal. We even survived COVID for 2 years. Because we have an immune system. So when you build a computer system or a smart system, like a smart grid is, you have to build the immune system. Of course, we are not in this class building the security part of it, but we are exposed to it. Security comes as a pain, as a penalty. It makes everything more complicated, more slower, but we have to accept it, and I hope to have convinced you a bit of that. In particular, because cryptographic methods are fragile, there is no proof that something is really secure other than the proof by experience, which means that software must be regularly updated, which is a pain. That means your PMU software that you did with IFT and DIFT and all the like, you will still need to patch it every few weeks because it uses TLS, for example. And if you remember, we saw this morning that TLS used the form of MAC then encrypt that is not very secure. Right? We should use a combination of MAC and encrypt that is secure. So if you were using that one, you discover it's not secure, then you should change it, which normally is not your problem. If you install software, it is provided by National Instrument, for example, or Microsoft, or etc. Then it will naturally come with updates. Passwords must be frequently changed and must be different for every site. In particular, passwords are the fragile part of it. When I have a public key and a private key pair, for example, my private key is stored in my computer. It's protected by a password, and my computer is also protected by a password. If I don't protect my computer well, then somebody will be able to hack into it, therefore get my private key. So all this cryptography thing works as long as the passwords are correct and are not easy to find, which means two things: change them every year and have different passwords for every site. That's from one person's viewpoint. So from my viewpoint, if I use a password on different systems, I should have a different password on a different system. Why? Well, because any of those systems one day can be compromised. So if I lose one password on one system, I'm not losing all the systems I'm using. And vice versa. If several people are using the same system, in industrial network like electrical systems, that's particularly true. Assume you're deploying a PMU software or a PDC software. This is, of course, there's a password to go in the machine. Whose password is it? Is it the password of the PDC called PDC1, or is it the password of a user who logs into the PDC? Very often, still in industrial networks, people use, like we do in the lab, by the way, when you log onto the virtual machine, you put the virtual machine is called LCA2, and the password is LCA2. In reality, if you do it in real life, you will need to have a password like you do when you connect to the EPFL network. You don't connect to the EPFL network with a password that is common to all students of electrical engineering, for example. You have your own individual password. Even if you're connecting to the same resource, you're watching a video or something that is encrypted or accessing some resources on Moodle, you need to have a password which is per person, right? Not per device here. Because you must be able to repudiate a person if somebody becomes suspicious because somebody did an attack or was crappy, had his password lost, stolen, then we can repudiate this password and not the system here. And last, if you have to deploy security solutions, which many of you will have sooner or later, not that you will invent a security solution, but you will need to deploy, for example, a streaming application that sends the data from PMU to PDC. You will have to deploy it with TLS typically, or DTLS. And then you have to verify perhaps through resources online. NIST is one of them. That's the American Standards Organization. That's every hour updates what are the compromised softwares and what are the ones that are still valid. Well, it's a bit paranoid, but it's very mildly paranoid compared to the level of the attacks that are out in the real world. Well, that's all for the lecture part. Now you have still to do the quiz. We have this chaining system. You do a quiz every week in principle. We try to incentivize it to do by small pieces. Learning goes better. It's like eating a big apple pie. If you have to eat it all at once, probably you will not digest all of it. So it's better to do by small pieces. So we insist that you do one quiz every week and also the labs. This lab for this year lasts 2 weeks. You've observed it's a bit bigger. So it's doesn't mean it should do it at the last minute next week. It really takes 2 weeks to do it. Yes, question?
The session of Friday for the lab is the same lab?
It is the same lab, exactly.
So we have office hours?
We have office hours on Friday. You can bring your question. You can post the question anytime, not just on Friday, by the way, but if you want personal coaching, you can come on Friday prepared with your questions. Thank you very much. That's the end of this module. So next week, Mario will take over, and then we will meet again in 4 weeks to discuss optimal power flow and more electrical things.